So what we're saying is that the universe is currently this big, and that sometime earlier it must have been this big, because it has expanded to this size. Well, that means that at some time earlier it was even smaller and has expanded. And that means that at some time before that it was just a point. And that is what we call the Big Bang. What caused the Big Bang? We don't know. It's no use saying that it was a fluctuation in gravity or a quantum fluctuation, because that begs the question, what caused the gravity and what is the cause of quantum fluctuations? We just don't know what caused the Big Bang. But we do believe that the universe is expanding. But what is it expanding into? Some people think that the material in the universe is expanding into a big space. But that isn't actually true. Space is itself expanding and carrying all the material in the universe with it. Consider the surface of a balloon. And let's imagine that there's an ant living on the balloon. The ant only understands two dimensions. He can understand back and forth and side to side, but he can't understand up and down. He has no concept of volume. He spends his days walking over the surface of the balloon. And let's imagine that there are points on the balloon. The ant can walk between the points and indeed measure the distance between them. Now imagine that we blow the balloon up. All those points on the balloon will now be further apart, and the ant will measure them as being further apart. When we say, "What has your universe expanded into?" he won't know. He doesn't understand volume. All he knows is that the points have expanded, and so has the fabric of the universe, which in this case is the surface of the balloon. It's all expanded, but it hasn't expanded into anything. Time and space were all created at the Big Bang. Space expands and carries all the galaxies and stars with it. But how fast is the universe expanding? Could it be that if I were talking to you, we would be moving apart as space expands? Well, let's consider 2 points 1 meter apart. How does space expand between them? Well, the velocity we know is hd. That is Hubble's famous law. The velocity, therefore, is h, which is 3 times 10 to the minus 18, times the distance, which is 1 meter. And that gives us a velocity of 3 times 10 to the minus 18 meters per second. So every second, the space between 2 points 1 meter apart would increase by 3 times 10 to the minus 18 meters, which is 1,000 times smaller than the diameter of a nucleus, so barely noticeable. And in any event, space does not expand in what we call bound systems, like the Earth, or indeed the solar system, or probably even our own galaxy. Space expands principally between galaxies. But let's see if we have 2 points that are in fact 1,000 light years apart. A light year is approximately 10 to the 16 meters. So 1,000 light years is 10 to the 19 meters. Now v is h, which is 3 times 10 to the minus 18, times d, which is 10 to the 19, 1,000 light years. And that's 30 meters per second. What happens if the points are 1 million light years apart? 1 million light years is 10 to the 22 meters. 1 light year is 10 to the 16 meters, and 1 million of them is 10 to the 22nd meters. that means that the velocity, in other words the relative speed between them, will equal Hubble's constant, 3 times 10 to the minus 18, times 10 to the 22. And that's 30,000 metres per second. And that's quite fast. How old is the universe? Well, let's imagine that it's T years old. And let's consider that from the Big Bang, 3 objects emerged and have been travelling for the whole of the time t. This has travelled a distance d1 at velocity v1. This has travelled a distance d2 at velocity v2. And this has travelled a distance d3 at velocity v3. What can we say? Well, we can say that distance is speed or velocity times time. So d1 must equal v1 times time, which is of course the age of the universe. d2, which has been travelling from here to here since the universe began, equals v2 times t, and d3 equals v3 times t. Or more generally, the distance that an object has travelled is equal to its velocity times the age of the universe. And so d over v equals t. But we know from Hubble's law that v equals hd, which means that d over v is 1 over h. And that means that t is 1 over h. So the age of the universe is 1 divided by Hubble's constant, which is 3 times 10 to the minus 18, in seconds. How many seconds are there in a year? Well, there are 365 times, that's days, times 24 hours, times 60 minutes, times 60 seconds, which comes to approximately 3 times 10 to the 7 seconds in a year. So if we want to convert seconds into years, we say that t is 1 over 3 times 10 to the minus 18 times 3 times 10 to the 7, and that very roughly comes to 10 to the 10 years, or t equals 10 billion years. And that's the age of the universe. If you do the calculation a little more accurately, you get 13.7 billion years as being the time from the Big Bang. There is a big assumption in that Hubble's constant h has been constant throughout that time. That may not be the case, but if it is, then the age of the universe can be calculated to be 13.7 billion years.